Hi everybody, it's crazy, it's Monday, and it's time for the UPBGE video of the week. Now, before I get started, gotta get a shout out to my trusted, because you guys rock, to my crazy fam. I love you guys. Now, we're up to episode number 120. That's quite a bit of an end to this, haven't we? Now, last week we left off on page 34, and I'm gonna switch over to here so you can see what I'm talking about. Internal functions is what we're going to be doing today. So I guess let's just get started. Okay, so the file we left off with last week was also navigation, camera navigation.blend. Okay, so that way you can see, you can move around with the camera. We have orbit view, you have walk view, and fly mode. Okay, and over here you'll see that it shows changing cameras. That's what we're going to be talking about today. Okay, so internal functions, scripts.move camera underscore move, or I'm sorry, scripts.move underscore camera, scripts.orbit underscore camera, and scripts.look camera. Okay, so basically we're going to have the move camera, then we're going to have the orbit camera, and then we're going to have the look camera. Okay, so these three functions are called from the event management functions. In their lines, you can find the math responsible for the camera movement. We're calling them internal functions because they are the bridge between the sensor inputs and the outputs in the game engine world. So sensor inputs and outputs because we're using Python. Okay, let's see. Yeah, scripts.moveCamera, the function responsible for the camera movement, is very simple. In the walk and fly mode, we are going to move the pivot in the desired direction, which is passed as an argument. Therefore, we first need to create a vector to this course. If you are unfamiliar with vectorial math, think of vector as the direction between the origin 0, 0, 0 and the vector coordinates x, y, and z. Okay, and that's going to be down here at 336. Let me get to it. 336, which is right here. Okay, which is move camera. Okay, so the move underscore camera, which is the definition we're going to be starting with first. Okay, then you've got if not g dot cameras cam equals move return move equals 0.5. Okay, that's the speed. All right, so basically what it's saying is if not in G camera's camera, then it will equal, okay, none, or move, I'm sorry, it equals move. So if it does equal move, you're going to return move equals 0.5. If direction equals 0, okay, going forward, vector equals m vector 0, 0 move. And it's going to have this to 0.25 added to right here, but it's going to be minus it. Okay, it's got a little minus right there on the front, right before that m. Okay, elif direction equals 1 backward, vector equals m vector 0, 0 move. Okay, which is the standard 0.25 forward. Okay. All right, so elf direction equals 2 equals left. Okay, the vector is going to move. Okay, on the x-axis, not the and not the z-axis. Okay, so it's going to move on the x because x, y, and z. Okay, so these are going to stay in the center, and it's just going to move on the x-axis in a negative fashion because there's also a little negative right there. Okay, oops. Okay, LF direction equals 3 goes to the right. Vector equals m dot vector move, which is no minus sign, 0, 0. So that means it's going to move it 0.25 to the right. Okay, so each one of these is going to give a direction. Okay, every time you press a key, the camera is going to move in that direction, 0.25. Okay. Let's see, now we're going to go down to 56, which is this little guy right here. Okay, now that we've calculated the vector, we can move the point. To be continued in the game interaction section. Okay, so we're going to continue this on in the interactive section, but these are what it is right here. Okay, It's basically moving the pivot point on the move, okay? And it's using the 2, which is up here, which was 2 would be to the left, okay? A pivot dot apply movement vector equals true, okay? Is true. All right. Here, the vector is the movement we need to apply to the pivot in order to get it moving. Size of the vector move will act as intensity or speed of the movement. Scripts.orbit camera. We decided to use different methods for the walk-fly camera and the orbit one. In the orbit camera, every position on the screen corresponds to an orientation of the camera. If you want to study this part of the script in particular, you can turn on the mouse cursor in the render panel. That way you can see that the same cursor position will, or should, always generate the same view. And that's at 224. We're going to go back up here to 224. Right here, okay, that's defining the orbit camera. Okay, we're going to get the screen size, which is screen width and screen height. All you got to do is get R, okay, which is, if you remember, way up here, okay, as R, we're going to have render, okay, and, okay, so render dot get width, window width, and get window height. Say that 5 times fast if you can. Okay, so we're gonna get the screen, get the screen height, and get the screen width. Okay, and then when X, okay, comma, when Y equals sensor position. Okay, so your window screen, okay, now we've got it, okay, is going to have the X position and Y position on the screen because you don't have a Z here, okay? It's just left and right, up and down, okay? All right, so g.orb.clamp, okay, and they had changed this up a little bit. Orb limits, okay, because they took the g.orb underscore clamps is in radians, okay, so they took that out. Oh no, it's right there. Okay. All right, never mind. I just read it wrong. Okay, so orbit limits equals g.orb limits. Okay, left limit is going to be orb limits left, orb limit right, orb limit bottom, orb limit top. Okay. Normalizing X to run from left to right limits. Okay. So we got X equals when underscore X screen width, and then X equals LF, or left, I'm sorry, LF, the left underscore limit plus X times R underscore limit minus left limit. Okay, so what it's going to do is it's going to get the right limit. It's going to time X, okay, whatever X is, okay, which would be this guy right here. Okay, it's going to times that, which is your left limit. Okay, it's going to times that by the right limit minus the left limit. So basically, it's going to take off the right limit, so that way it goes further to the left like it's supposed to. Okay, and then we go normalize, okay, Y to run from top to bottom limits. Okay, Y equals when Y and screen, or divided by screen height. Y equals top underscore limit plus Y times bottom limit minus top limit. So it's going to do the same thing as kind of what this did, but it's going to do the top and bottom. Okay. Flip the vertical movement, which is right here. Y equals m dot pi divided by 2 minus Y. Okay. So that's all these right here. That it's going to do this Y right here. It's going to divide it by pi. Okay, it's going to divide, Y will equal that with whatever Y was. Okay. All right, so calculate the new orientation matrix. Okay, matrix.orientation equals g.cameras orb. Okay, 1 orientation. mat x equals matrix dot rotation x3z. Okay, and then mat y equals m dot matrix dot rotation y3x. Okay, ori, okay, which I'm pretty sure is orientation, equals mat x times mat y. So what it's going to do is get these two and times them together. Okay, that's going to equal your full orientation. Okay, and then you've got, see, yep, and then you got your pivot. Now you do your pivot, which equals g dot cameras orb 2 pivot dot orientation equals orientation. Okay, now we can use ori as our new orientation matrix. To be continued in the game interaction section, which is this guy right here. Okay, the first lines that deserve our attention here are the normalizing operation. To normalize a value means to convert it to a range from 0.0 to 1.0. In our case, it can be understood as the mouse pointer coordinates relative to the screen dimensions, width and height. Okay, so 242 would be up here. Okay, that'd be this little guy right here. Okay, x equals win underscore x divided by screen width. Okay, even fewer logic bricks and normalized mouse coordinates. It's important to always use normalized coordinates for your screen operations. Otherwise, different desktop resolutions will produce different results in a game. It's very important, okay, because you want to make sure you have your screen width and height matched to your player's screen height, okay, or you set a certain resolution for that, and it'll go from that, okay. As a counter edge case, you may need the absolute coordinates for mouse events if you want to assure minimum clickable areas for your events. You don't always need to normalize the mouse coordinates manually. Like the keyboard sensor, you can replace the mouse sensor by an internal instance of the mouse module. The coordinates from bge.logic.mouse run from 0.0 to 1.0 and can be read anytime. You can even link your script to an always sensor, leaving the mouse sensor for the times where you are using more logic bricks. You can read about this in the bge.logic API section in this chapter, or on the online API page, which you should have that. If not, it's in the book, which you should be reading right along with me. You can also find the files also that come with the book, and you'll see up here that I'm actually using a file from the book. Okay. Now, a simple operation to convert the normalized value to a value inside our horizontal angle range, which is negative 220 degrees to 220 degrees, okay, which is 243. Okay, so if we look at 243, where you at? I know it's on your side. It is. Okay, so the left underscore limit plus x times right underscore limit minus left underscore limit. Okay, we run the same operation for the virtual coordinate of the mouse. Though you must be aware that the canvas height runs from top 0 to the bottom height. This is different from what we could expect from OpenGL coordinates, for example. In order to better understand the flipping operation, line 257, which is right here, okay, you can first comment or uncomment the code to see the difference. Okay, so you can comment this out, which is hitting the little shift 3, which gives you that little, makes everything green. Okay, or you can uncomment it, is what it's talking about. Next, find the .blend file in the pivot empty orb._pivot. okay, and play with this rotation in the x-axis. The rotation is demonstrated in figure 11. Therefore, or 7.11. Therefore, if we subtract our angle from 90 degrees, pi minus 2, in radians, we get the proper angle to rotate the pivot vertically. Okay, y equals, and that's right here. See, nope, that's not right there. That's, where was it at? I had seen it. Oh yeah, right here. Okay, that's this little guy right here. Okay, that one is what makes that work. Okay, and I may have to shrink that down so you can see it a little bit better on one screen. Let's flip over here. Now you see you got 0, 22.5, 45 degree angle, a 67.5, and a 90 degree angle. Okay, that's what you see, or should see, if you're running it the way it should be running. Let me kick that back up so I can go back down. Okay, scripts.look camera, that will be on 290, okay, which is right here. Okay, that little guy right there. Oh, 291. Now they've got it they actually added something in, so it actually got kicked to 292 instead of 291. But I'm gonna go ahead and read on. The function to rotate the walk fly camera is quite different from the orbit one. We don't have a direct relation between mouse coordinate and camera rotation anymore. Here we get the relative position of the cursor from the center, and later force the mouse to be recentered to avoid continuous movement unless the mouse is moved again. In order to get the relative position of the cursor, the normalizing function needs to be different. This time we want the center of the screen to be 0.0 and the extreme edges of the canvas border of the game window to be -0.5 and 0.5. Okay, so as you see, scoot that up, you got 0.5 and -0.5, which is right here. Okay, when the values of x, okay, and y can be used directly as radians, angles, to rotate the camera. However, when we are walking, we want to restrict the view vertically. This design decision means that we need to limit the view angle to a maximum and minimum range. Sure, this turns trying your shoes into a circus challenge. Though it may seem like overkill, this limitation helps add a better sense of reality to our navigation system. The solution is to get the current camera vertical angle and see if by adding a new angle, i.e. vertical mouse movement, we would end up over the limit of 45 degrees. If so, we clamp the new angle to respect this value. Okay? We would end up over the limit of 45. Okay, so if so, we clamp a new angle to respect this value. To get the vertical angle, remember that the camera pivot, an empty object, is always parallel to the ground. Therefore, the vertical angle can be extracted from the camera's local orientation matrix. If that still doesn't make sense to you, try to find some 3D math tutorials online. And trust me, if you want to learn a little bit more about this, then I would suggest you do that. Math is very important. Even though I sucked at it as a kid and adult, finding some tutorials on working with math really would help. Okay. And then 302, which is the next one we're going to go over, which is rotate the view. Oh, that's 312. I'm sorry, my bad. There you go. All right, yeah. Limit top minus bottom angles. Okay, is what we're going to be doing next. Okay, and of course we're going to go on straight on down to 9. So basically 9 will be the end of it right there. Okay, for the actual project, this will originally was originally designed for, we ended up moving the orbit camera mode to be a subset of the walk fly. Having the mouse always centered comes in handy when you have a user interface on top of that, and it needs to alternate between mouse clicking and camera rotating. Although the methods are different, the results are the same. Alright, so that's going to end it for there. What are we at? Ooh, we did a 20-minute video today. Okay, so that ends that part of it. Now we're going to get into the game interaction next week. Okay, so let me check out of that and that. Let's kick back over here. So that is actually at the bottom of page 40. Okay, game interaction is what we're going to be doing next week. Also, go online, look 3D math, okay? Hang on, let me get back up to it so I can remember what it said. 3D math tutorials, okay? Look them up, do some videos, get you a book. I started out with the Python books, and since this is a book that we're doing, you can go back over different areas and try to help yourself out and retry them over and over again until you get them. Sometimes that's the best way you can actually get it to where you can do stuff, okay? So we're going to go ahead and leave it there. Game interaction next week, page 40. See you then.